Hi, welcome to AB Video 2.3F Part 1, Acceleration. So we're going to be going back to motion and also the normal line, which is related to the tangent line. Okay, so just to recap for motion, we've so far been looking at vertical motion, dropping or tossing something from an elevation. We're also now going to be looking at horizontal motion. So in general, motion, you have a position function, S. If you're talking vertical motion, S being the distance from the ground. If you're talking horizontal motion or on a horizontal line, we'll pretend that that horizontal line is a number line, and the S would represent the distance from the origin on that number line. And the T, of course, represents time. The velocity is V of t equals the derivative of S of t, or ds dt. For vertical motion, if the velocity is positive, the object is moving upwards. If the velocity is negative, it's moving downwards. So as you can imagine, for horizontal motion, if the velocity is positive, we're moving to the right. Think of as you're in drive in the car. And then if the velocity is negative, you're moving to the left. Think of that in a car as moving in reverse. So, again, and this is something we'll be looking at a lot in Chapter 3, if you look at a graph F, this red graph F is increasing, then decreasing, then increasing. Remember, we always look at the graph's behavior from left to right. Well, you'll notice if I was to draw a bunch of little tangent lines, wherever F is increasing, the tangent lines will have a slope that's positive. The slope of the tangent line will be positive, so the first derivative is positive. Whenever the red function f is decreasing, you'll notice all these little green tangent line segments have negative slopes. And again, f is increasing, the slopes are positive. So if the slope is positive, if the first derivative is positive, then the function is increasing from left to right as x increases. If the first derivative is negative, then f of x is decreasing. So, again, all of this is everything we know. Velocity will be, for example, in feet per second or meters per second, could be miles per hour. And what we're going to introduce now is acceleration. So remember, the velocity is the rate of change of the distance with respect to time. The acceleration is the rate of change of the velocity with respect to time. So a of t, the acceleration at time t, is the derivative of v of t, making it the second derivative of the position function. So because the acceleration is a rate of change of velocity with respect to time, for example, the velocity might be measured in feet per second, the time is measured in seconds. You can either say feet per second, or you can say feet per second squared. This we already talked about. So this is page 129, number 118, an automobile's velocity starting from rest. So starting from rest means that the initial velocity is 0. And they give you the equation, so that's nice. So the velocity at any time t, starting from rest, is 100t over 2t plus 15, where v is measured in feet per second. So this velocity, this automobile's velocity, we're going to be doing that in feet per second. The question says find the accelerations at 5 seconds, 10 seconds, and 20 seconds. So remember, the acceleration is the derivative of the velocity function. So we're going to do a quotient rule on the velocity function. Acceleration is derivative of velocity, denominator squared, denominator times derivative of numerator, etc. Simplify, that's 200t minus 200t is gone. You're left with 1500 over 2t plus 15 squared. So if we do part A, they want the acceleration at 5 seconds. You're simply going to take the acceleration formula and replace the t by 5 seconds. And you will get 2.4, and again, that's in feet per second, because remember, it's a rate of change of velocity with respect to time, which is feet per second, or feet per second squared. Okay, so velocity positive implies the object's moving up or right, and therefore the distance is increasing from the ground or from the origin, and that happens when the derivative of the position function, which is the velocity, is positive. When the derivative of the position function called the velocity is negative, we already talked about this, that means the object is moving down or to the left, that means the distance is decreasing. We already talked about this as well. Now we're going to go on to the next level. So if we all agree that if the first derivative of f of x is positive, then f is increasing. So what I've done is I've said if the derivative of a function is positive, then that function is increasing. Well, if you do the same thing, if the second derivative of f of x is positive, which is the derivative of f prime of x, then f prime of x is increasing. If the second derivative is negative, then the first derivative is decreasing. Translation, look at it down here. If the acceleration is positive, then the acceleration being the derivative of the velocity, that would be from up here. If the acceleration, which is the derivative of the velocity, is positive, then the velocity would be increasing. If the acceleration is negative, the velocity is decreasing. Similarly, on the level before that, if the velocity is positive, the distance is increasing. So, for example, a vertical motion, if the velocity is positive, it means that the object is traveling upwards, therefore it's further and further from the ground. If the velocity is negative, it means it's traveling downwards, then the distance from the ground would be decreasing. Okay, so there is a worksheet here. I'm going to pause right here and pull up that worksheet. Okay, so let me have you look at this worksheet. Now, there's a few things on this worksheet. These are a couple of things that the book doesn't do a very good job of, or doesn't do at all. One of those is normal lines, which I'm about to talk about. Another one is when is the velocity zero, when is the velocity increasing, decreasing, when is the speed increasing, decreasing, and recognizing limits as derivatives. So I just want you to see this worksheet, okay? So it's an extra homework. I shouldn't say homework, but it's an extra worksheet to accompany section 2.3 in the Larson textbook. So notice the first 3 questions have to do with normal lines. The next bunch of questions, which start again at number 1, have to do with velocity being 0 and increasing and decreasing speeds. And then the last one is recognizing limits as derivative. And the last page does have the answers on them, okay? So we're going to look at the first one, which is normal lines, and let's go back and learn what those are. So the definition of a normal line is a line that is perpendicular to a tangent line at the point of tangency. So if you have this black curve and you have this red tangent line, and there's the point of tangency, if through that point you were to draw a green line that is perpendicular to that red line, that would be called the normal line. You can therefore call this the point of normalcy, although nobody does. Okay, so of course perpendicular, you remember from Algebra 1, means that the slope is the negative reciprocal of the other one. Well, it's perpendicular to the tangent line. The slope of the tangent line is the first derivative. So you just have to be careful when it says find the equation of the normal line to a function at a certain point. You are going to have to start with the derivative, which is the slope of the tangent line. So I'm going to find the derivative of 2x squared minus 8x, which is 4x minus 8. I'm going to find the derivative, which is the slope of the tangent line at x equals this 1, and I'm going to get negative 4. But of course, the line I'm looking for is a normal line. Its slope is going to be the negative reciprocal of the slope of the tangent line, so the slope of the line I'm looking for is a quarter. And of course the point is 1, negative 6, so x minus 1, x minus negative 6. Be careful you don't put negative 4 here. That would have been the equation of the tangent. And that's the end of video 2.3F, part 1.